Good evening everyone and welcome to my YouTube channel. So here today we are going to look at our microscopy video continuing. So we have the differential interference contrast microscopy. So now what are some of the things that it is made of? So the differential interference contrast microscopy has got a number of parts. We have the Nomarski prism, we also have the polarizer, we have the analyzer. So now the principle working of this is very simple. So firstly we have this one, the polarizer. So we are on our polarizer. So the function of the polarizer is to simply have more like one ray of we are talking about how the light rays are moving. Like for example, if you have, let's say the source of light is here, the way light might be moving in those directions, but the polarizer, when this light passes in a polarizer, let's say the polarizer is here, what begins to happen is that the light rays will now be able to start to move in just one plane, or rather more like you can just think of it as one direction like that. So the polarizer is important. Instead of light just moving at different directions, the polarizer helps for light to move in one plane. That is what we mean like that. Then when light moves in one plane, we also have this part which we are going to call the Nomarski prism. So this Nomarski prism converts, or not converts, but divides light into two rays. So remember, there was just more like one ray like that, but it is split into two like that. It goes the other side, the other one also goes on the other side. Now this light is split so that it is coherent. What we mean by coherent, it means to say it maintains the same distance throughout like that. Then even as it goes like that, it maintains the same distance. Not only that, but also the light is split orthogonal. When we say orthogonal, we simply mean to say it is split at right angles. So when the light is, so that's the function of the Nomarski prism. It is to, number one, convert the to divide the rays of light into two, and also to recombine. This is why we have this secondary Nomarski prism. So you can call this one as your first prism, which is your Nomarski prism, also the second prism, which is also called the Nomarski prism. So now with that said, we can be able to look at what happens. So the condenser, the function of the condenser is to more like focus the light rays. So when it comes here, the light rays are focused like that. So now remember, this was just one ray which has been split into two. Now the specimen, our specimen is this. Now let's say our specimen, which is this one, our specimen, let's say I have used red to denote that at this point our specimen is very thick. Then let's say at this point the specimen is not thick. So now what happens is that where it is thick at this point, the way light behaves is that light slows down where there is a dense medium. Now at this point the light will be able to move faster as compared to here. So here light will move slower. Now when it goes to the objective lens, it gets focused to the second Nomarski prism. So as you can see, there was the color green going like that. Then the other light goes like that. It is focused into the second Nomarski prism. So when it is focused at that point, the Nomarski prism now recombines the light. Now remember, these two rays were moving at different more like different parts of the specimen. Now the other thing that is very important for you to know is that the light that was divided here was just sheared, meaning to say the distance at which it was divided, it was very small, like it was just like a small distance, so that the light rays can just pass on the specimen at just different points. So where one light ray may pass at a point which is very thick, another one may pass at a point which is not thick like that. So as a result of that, when it gets recombined, it's more like now the light ray has been recombined, having where it was thick and where it was not thick. So now when it recombines, it comes like that. When it recombines, it goes, now we have to pass through the analyzer. So what our analyzer does now is that the difference in the phases. So at one point the image was thick, at another point it wasn't. So it is now able to, since the light rays have been combined, it is now able to convert these phase shift into intensity difference. Intensity, we mean to say the amount of light that you are going to see. So now let me show you how the image looks. So let's look. These are images that are produced by the DIC, which is our differential interference contrast. So as you can see, at this point, light passed through very fast as compared to this one. You can even be able to tell the thickness. So that is how the analyzer is able to get the phase shift and convert them into images. Where light passed very fast, it simply means to say it was less thick as compared to the other part. So this is how the images in DIC look. So they will look like that. We even have images like that. So we can even look at these other images. As you can see how the contrast is looking, where the light was passing faster, it is looking like less thick as compared to the other parts. So this is how the images for the DIC, you can even see the holes like that and everything. So this is how the images in DIC look. So the image formed 3D pseudo, we can call them pseudo 3D. So what we simply mean is that they are relief like. When we say relief like, how like the small mountains look, how the mountains look, something like that. You can even see especially this image. That is what we mean by pseudo 3D. So even the DIC can be used to view light, and there is no need for you to stain, since it is able to create the contrast that you need. And also your specimens could be a living specimen. So the resolution is about 200 nanometers. So that is it for the DIC. See you in the next tutorials. If you enjoyed the video, kindly like, subscribe and share for more.